Welcome to the new video where we are in the second video of the renal system, okay, the renal physiology. So basically in the first video itself we have covered like the basic anatomy of kidney, okay. Then we have covered this part only, okay, like we have covered the glomerulus, okay, the systems of the glomerulus, the various factors affecting that GFR kind of thing. We have covered that, okay, in the first lecture itself. Now after the glomerulus we have the PCT, okay. So the function of PCT is basically the proximal convoluted tubule. Basically it is concerned with reabsorption of sodium, water, glucose, then electrolytes, okay. This is the basic function, okay. So not going into the details of this PCT, okay, it is not too much important, but we should know that reabsorption is the main criteria, okay. Now this kind of thing, this one I just am highlighting this, okay. So basically this is the loop of Henle after the PCT. So covering the glomerulus PCT, now we are heading to loop of Henle. So what happens in the loop of Henle is the main process, which is the counter current mechanism, okay. The counter current mechanism, it basically concentrates the urine, or like it concentrates or dilutes, okay, the urine. The function of counter current mechanism is basically like that only, okay, to increase the concentration or increase the osmolarity or decrease the osmolarity, okay. The loop of Henle is concerned with that. Now in the counter current mechanism we will follow a series, okay. So the first is role of ADH, okay. The second is counter current mechanism. Counter current. Now you will say, what is this? The role of ADH and the counter current mechanism. Okay, so basically we will follow this two. And in counter current mechanism, basically we have three processes. The first is counter current multiplier mechanism, okay. Second is the role of urea, and third is the counter current exchange. So basically we are dealing with these three procedures, okay. So you will ask, what is this role of ADH, the counter current mechanism, why have you written like this? So basically you will understand this, okay. First discussing the role of ADH, okay. So in the first point itself we will write the role of ADH. So basically what does this ADH do? So ADH is basically anti-diuretic hormone, okay. So this anti-diuretic hormone, or also known as vasopressin, it basically what it does, it reabsorbs water, okay. It reabsorbs water from the collecting duct, okay. Reabsorbs water from collecting duct, okay. So why we are going in the collecting duct? Our main focus is loop of Henle. So basically the function of the loop of Henle is control the osmolarity or the concentration of urine. So now to control the osmolarity, the ADH also plays a important role, a pivotal role. So what it does, it reabsorbs water from the distal, like the collecting duct or the distal convoluted tubule. Then it increases the concentration of urine. So basically the role of ADH is also important while discussing the counter current mechanism. So hence we have discussed it here. Now the counter current mechanism, okay. The actual counter current mechanism. Counter current mechanism. Now the first mechanism in counter current mechanism is counter current multiplier mechanism, okay. So I will just mention counter current multiplier mechanism. So what is this counter current multiplier mechanism? This is the most important mechanism in this counter current mechanism. So let me just draw a bit diagrams and come in a few seconds. So now I have drawn this diagram. So what is this diagram? So basically this is a plain diagram of loop of Henle. So I will just label it. This is the descending limb, this is the ascending limb, and basically the thick part. Okay, remember this is the thick part. I will just rub it. This is not important for us, but important point was the thick part of ascending limb. Okay, now as the urine flows in the tubules, okay, I have also numbered the diagram for your reference. Okay, so this is the first diagram. So basically urine is flowing like this and it is going to DCT and the collecting duct. Now what happens is the urine is flowing at a rate of like means rate, no, it is not the rate, it is the like osmolarity. Okay, so osmolarity is 300 osmol per minute. Okay, the osmolarity of normal urine is 300 osmolarity, like it ranges from 300 to 1200. Okay, now as we have studied earlier, okay, long back in the first segment of this like the first segment of the first video itself, the functions of the loop of Henle. So the descending limb, okay, so this limb is basically, it is responsible for, like, it is permeable to H2O but is impermeable to solutes. Okay, so let me mention it, like did we mention it here? No, we didn't mention it here. So let me mention it here. So basically just I will write it. Descending limb, okay, so descending limb and ascending limb. Okay, so basically descending limb is permeable to H2O and impermeable to solutes, and ascending limb is just the opposite, it is impermeable to H2O and it is permeable to solutes. Okay, now this concept will be applied here. Okay, so now what happens is the osmolarity is 300 osmol per minute. The 300 osmol per liter is the osmolarity. Now what happens is, since the ascending limb, and basically we are talking about the thick ascending limb, it is permeable to solutes. So some solutes will be removed like this. Okay, I forgot to mention the osmolarity here to 300. Everything is normal. Okay, so basically in the second figure, some solutes are removed from the ascending limb, thick ascending limb. So since solutes are removed and water is more than solutes in the ascending limb, so the osmolarity decreases. So basically the osmolarity will become like here, it will be 300. Okay, and since water is removed, oh sorry, the solutes are removed and water is present here, so the osmolarity will be somewhat like 200. Okay, and it will then flow 200 also. Okay, now since solutes are removed from the ascending limb, okay, now tell me one thing, if solutes are removed here, like the solutes are removed from here, so the osmolarity is decreasing. Okay, it is becoming 200. Where the solutes come? So in this part. And what is this part? This part is the renal medulla. Okay, since the loop of Henle is present in the medulla, so this is the renal medulla. Now the osmolarity of the medulla increases. Okay, here it was 300, here it becomes 400. Okay, 100 is gone from here 100 is received here. Okay, so what is happening? Basically the sodium or some solutes are getting like out from the renal tubule or the ascending limb, thick ascending limb. So basically the osmolarity of the renal medulla is increasing and the osmolarity of the ascending limb is decreasing. Okay, now coming to the third figure. So what happens in the third figure? We have the osmolarity like 400, 400, 400. Okay, and here it is like 200, 200, 200. Okay, somewhere here it is like 300. Okay, so now what happens is, we have studied that in this descending limb it is permeable to H2 and impermeable to solutes. So what happens is, the descending limbs removes water and it is permeable to water. So since water is removed, okay, so the osmolarity of this descending limb, what it will be become now? Yes, from 300 it will be 400. Okay, somewhat like this, it will be 400 and the earlier osmolarity was 300. Okay, now tell me one thing. If this is the case, okay, now what happens is, the urine or the like water is not stagnant in the body, it keeps moving. Okay, so water will come from the glomerulus, like it will not stop in the glomerulus or the PCT itself, it will continuously flow in this loop of Henle also. Okay, so it will come like this. So the new water which is coming is 300 osmol per minute. Okay, so the new water from the PCT or the glomerulus is coming in the loop of Henle. Okay, so it is 300 osmol per liter. Now basically the new water is 300 osmol per liter. Now the earlier water was 400 osmol per liter. Okay, basically we are not talking about water, it is serum. Okay, so basically the earlier serum was 400, so that 400 will be pushed. Okay, due to that new water or the new serum, the 400 will be pushed downwards. Just a second. So the 400 osmol basically will be pushed downwards and it will go to the ascending loop. Okay, and the 200 osmol will also be pushed and it will go to DCT. Okay, now what happens, this 200 osmol and this 400 osmol which is now in the ascending loop, okay, will further like 200, just a second. So what happens is, more solutes are removed from the ascending limb, the thick ascending limb, and now this 200 will become 150. Okay, let me use a different color for less osmolarity. So basically it will be 150 and the 400 will convert to 300. Now you will think, why I am like from the first, okay, I am more concerned about the osmolar gradient. Okay, so basically the gradient is 200. Okay, the gradient is 200. Okay, gradient is 200 between the like the renal medulla and the loop of Henle. Okay, so the 200, let me also write the unit, 200 milliosmol per liter. Okay, so basically it is 200 milliosmol per liter. This all is not osmolar per liter, basically it is milliosmolar per liter. Okay, so the gradient is 200 milliosmolar per liter. So we are maintaining this. Okay, in this also we have maintained it. So if there is 150, okay, so it will be 350 here. Okay, and if it is 300, okay, so basically the 400 is converting into 300, so here it will be 500. Okay, Now here comes the catch. Okay, so basically this will be same 300, 300, new water is coming continuously, so 400, 400, and then it will be pushed. Now tell me one thing, if I repeat this procedure, like now it is 150 and 350, 300, 500. So if I repeat 5 to 6 cycle, or let's say around 4 to 6 cycles, so I will get some values like this. Okay, 1200, 1000, 700, 300. Now repeating this cycle will cause, like, the values will be like this in the medulla, okay, renal medulla, and the values in the loop of Henle will be somewhat like, see here it is 12,000, oh sorry, it was 1200 or 1200, so here will be 1000. We are maintaining the osmotic gradient. Okay, so if here it was 1000, here will be around 800, 700, so 500, 300, so 100. So basically we are maintaining the osmotic gradient, and basically maintaining the osmotic gradient. Now tell me one thing, the urine was coming, like it was coming from the body, or the serum was coming from the body, like 300 milliosmol per liter was the concentration. Okay, and we have reduced it till 100 milliosmol per liter. Now there is one point to note. Okay, let me just highlight those points. So this renal medulla, I will just highlight the renal medulla. This renal medulla was 300 milliosmol, okay, and it converted to maximum of 1200 milliosmol. Okay, so basically the concentration increases. So this renal medulla is also known as hyperosmotic renal medulla. Okay, so now tell me one thing, what we have done, we have decreased the concentration of urine. Okay, now if I want to increase the concentration, okay, there are two ways. The two ways are, at the first way is basically I can, like, if I want to increase the concentration, okay, so basically I will do what, I will basically in the first figure itself, or the second figure we are talking about, we will reabsorb less solutes, or we will, in the third figure, we will reabsorb, like we will lose less water, more water. Okay, so these are the ways. And the second way, basically we will now write the second way. So basically we have completed with that counter current multiplier mechanism, where we maintain a osmolar gradient of 200 osmolar per liter. The thick ascending limb is permeable to solutes, so solutes are removed from it. The descending loop is basically permeable to water, so water is removed from it, and we get a concentration gradient. Okay, and the 300 milliosmol per liter urine is converted to 100 milliosmol per liter and excreted into the body. Okay, now the counter current multiplier mechanism is done. So we are in the state of discussing the role of urea. Okay, so the role of urea. Now what happens is, the role of urea, let me just again draw that loop of Henle. Just a second, I will come. Okay, let me just complete this figure. Let me also show the collecting duct. Okay, so basically this is the collecting duct. So what happens, urea is somewhat present here, okay, in the collecting duct itself. So if there is there is increased concentration of urine. Okay, so basically what happens, just a second, so this urea, when there is increased concentration of urine, so basically this urea is a solute. Okay, so this urea is removed from this collecting duct and it is gone to the the renal medulla, the hyperosmolar renal medulla. So basically concentration of urine is decreased in this case. So this was the role of urea. Now the vasa recta, okay, the counter current exchange. So now in the counter current exchange, let me just come in a minute. So now I have purposefully drawn this diagram. So what happens, this is the loop of Henle, okay, this is the loop of Henle, and this is the vasa recta. So what happens is the urine is coming like this, okay, or the serum is getting like this and converting into the urine, and the flow in the vasa recta is like this, the reverse flow, okay. Now this was one concept, the flow of loop of Henle and flow of vasa of recta. Then I will just let me draw one more diagram, then I will come in a bit. Now in the vasa recta we have learned the flow is like this, okay, and the osmolarity of plasma is approximately 300 milliosmol per liter, so we have to maintain that. Now remember what happens in the vasa recta in this limb, okay, particularly this limb. What happens, the solutes, okay, solutes are basically added, okay, solutes are basically added. Let me write solutes, okay. So solutes are added and water is removed, okay, and in this limb particularly the solutes are removed, okay, and water is added. Now this H2O extra, this is an extra H2O, so where does it come from? So basically it is the H2O from the, see this diagram where we have removed H2O, yes, in this diagram we have removed H2O. So basically this H2O, the extra H2O in this vasa recta comes from descending limb, and therefore this is the main reason why the gradient increases. If the gradient doesn't increases, basically the difference, okay, we starts from 300 and it till goes till 1200. So basically this extra H2O is coming in that ascending limb of that vasa recta, this one, okay, and basically it goes like this. So tell me one thing, now the concentration will be like 300, okay. Now solutes are being added and H2 is removed, so the concentration increases, so 500, 700, then 1000, and it will come till 1200. Now tell me one thing, if H2 is added and solutes are removed, so the concentration will again decrease, so it will be like 1000, 500, 300, it may reach till 100 also, okay. So this was about the counter current exchange. Let me just, I forgot to mention the heading. This is the counter current exchange, okay. So basically we have completed the counter current exchange, okay, the role of ADH. Yes, I would like to add one point. Let me just draw one nephron like this. So now what happens is, we have studied that the urea is present here in the collecting duct, okay. So now this urea is transported, there are, just a second, there are urea transporters, okay, these are the urea transporters. So urea is transported here in the hyperosmotic renal medulla, and thus the urea is overall responsible for, yes, decreasing concentration of urine. So basically if solutes are removed and water is more, so concentration is automatically decreased. Now exactly opposite function is done by ADH. So basically if ADH is acting, Okay, so ADH acts on the late DCT. Okay, let me just write it here, acts on late DCT and collecting duct. Okay, so basically ADH is acting on that late DCT and collecting duct. It will absorb water. Okay, so H2O will be removed, and since this H2O is removed, okay, what it will do, H2O is removed and the solutes are more, so increase in concentration of urine. Okay, so for example, if you drink more water, okay, more and more water, so what happens, you tend to urinate more. Okay, so basically that tending to urinate more is basically due to this urea. Okay, if you drink more water, so the urea will be removed. Okay, urea will be removed, like the solute will be removed and excretion of more water will occur, so the concentration of urine is less and the output of urine is more. Now if you drink very much less water, okay, so what happens is your like the pituitary, the posterior pituitary basically releases ADH or vasopressin. It acts on the late DCT and collecting duct. It reabsorbs water from the collecting duct and there is increased concentration of urine. Basically the urine output is decreased. So this is how the urine output is regulated by these two mechanisms. Okay. Now let me just summarize things. So basically we started from the glomerulus. Okay, the glomerulus, what is it, is the glomerulus and the Bowman's capsule. Okay, Malpighian body basically. So what is it responsible for? The GFR, glomerular filtration rate. Okay, so we completed the glomerular filtration rate, then we proceeded to the PCT. Okay, the PCT is responsible for reabsorption of sodium, electrolytes, solutes, water, glucose. Okay, so basically reabsorption work is done in the PCT. Then we ascended to loop of Henle, the counter current mechanism, in which we studied about the role of ADH in counter current mechanism, the role of the counter current multiplier mechanism, then the role of urea, and then finally the vasa recta, the counter current exchange. Okay, so we completed the the glomerulus, PCT, then the loop of Henle. In the distal convoluted tubule and the collecting duct. Okay, the distal convoluted tube is basically it is if water is we want to reabsorb water, okay, actively, so the ADH will act and water will get reabsorbed in the DCT, and same with the collecting tubule. Okay, late DCT and collecting tubule. So basically the DCT is responsible for reabsorption of water. Okay, active reabsorption of water if necessary, and then the collecting tubule is also responsible for absorption of water as well as the absorption of urea. Okay, and why we show this? Okay, this one, why we show this? So basically many collecting ducts opens into a main collecting duct, and the main collecting duct will go to the renal pelvis. So this is how we have completed the whole new nephron. Okay, sorry, it is nephron. Okay, so basically our journey started here. Let me use a brighter color. Okay, our journey started here in the glomerulus. Just a second. Journey started here and we got to the PCT. Okay, then the DCT, sorry, in the the loop of Henle. Then we jumped to this DCT and the collecting duct. Okay, and also we have covered the tubuloglomerular feedback, okay, in the glomerulus itself, and the juxtaglomerular apparatus or the juxtaglomerular cells. Okay, and together the juxtaglomerular cells and the macula densa cells, they together form the juxtaglomerular apparatus. Okay, so that's it for today's video. We have completed the nephron fully. Okay, so we have completed all the nephron. Thank you.